Hi everyone. So in the previous video, we have derived equations to relate the pressure, translational kinetic energy, temperature, and root mean square speed. So in this video, we'll be focusing mainly on energy. To be more specific, we'll study how translational motion, rotational motion, and vibrational motion contribute to the internal energy of gas. So we'll be doing this using the principle of equipartition of energy and the concept of degrees of freedom. So let's get it started. In the previous video, we have learned that the translational kinetic energy of a gas molecule is equal to 3/2 kBT. kB stands for Boltzmann constant, T stands for temperature. So this translational kinetic energy here is the translational kinetic energy of one single gas molecule. So right now what I'm going to do is I'm going to split this into three parts. Three equal parts of half kBT plus half kBT plus half kBT. Why do I do so is because based on really complicated statistical analysis, we have figured out something called the principle of equipartition of energy. So let me write down the definition first. So through statistical analysis, we have found out that the 3/2 kBT that we have for translational kinetic energy, actually it is made up of three equal parts of half kBT, right? So why do we have this 3/2 kBT? This 3/2 here actually comes from the fact that it's because a gas particles for translational motions can move in three different dimensions: the x dimension, the y dimension, and the x dimension. And it's because they have three different dimensions that we can split into three equal parts of half kBT. So let me use some drawing to probably illustrate what I'm trying to say. So you have a particle, and this particle has the ability to move to the left. Okay. At the same time, this particle has the ability to move upwards or downwards, which is the y direction. And lastly, you have the ability to move in the z direction. Okay. So these are three different directions, and because this translational motion, it has the freedom to move in these three different directions. Okay, so we will have three times of half kBT. So each of the direction here, each velocity component here, one is Vy, one is Vx, one is Vy, one is Vz. Each of these velocity component will contribute to half kBT of kinetic energy per molecule. But this is on average. So let me change a bit the equation that I have here to reflect average. So I'm going to remove this thing here. But I'm going to say this is because of kinetic energy on average. So this pointy bracket here represents average. So let me be very clear. How do we get these three things? Is they come from translational kinetic energy. Okay. So these three directions here are the possibility that how every gas particles will move in space. It's either x, y, or z. So let's say if I have a gas particles here, the Vx will be in this direction, the Vy will be in this direction, and the Vz will be in this direction. So three different directions that the particle has freedom to move. So we call this kind of direction that it's able to move, we call it degrees of freedom, the freedom to move. Okay, so these three are available for every kind of particles, but we'll start from writing it as monoatomic particles. Okay. So for monoatomic particles, you have a degree of freedom, which I call it as F of equals to 3. Okay, so let's proceed. Let's say you don't have just one single gas particles. Let's say you have two particles forming a gas molecule. In this case, besides moving in the x direction, y direction, and z direction, the particle also have the ability to rotate. So how many types of rotation? First, you can have rotate that looks like this. Rotation that looks like this. The second type of rotation is you rotate like this. Okay. So for this rotation like this, the axis will be pointing upwards in the y direction. So another rotation will be like this. So for the rotation like this, our axis will be pointing in the z direction. So two additional degree of freedom for us to move if we have more than one particle forming the gas molecule. So let me write it down. So you have the gas particles. First is it's rotating in this axis. So I'll call this to be omega in the y direction. The second one will be you have the particle rotating in this dimension here, and this is the z dimension, so I call it omega z. Okay, so these are two different rotational axes that the particle is able to rotate. So as usual, because you have new velocity component, now your velocity component here is omega y and omega z. Previously is vx and vy and vz. So now because you have two additional velocity component, then these two velocity component contribute another 2 units of half kBt. So you can add on half kBt plus half kBt. And this 2 half kBt is due to the rotation of diatomic molecules. So right here, this is contributed by diatomic, the properties of it being diatomic. Okay, if it's just one, you will not be able to rotate in any axis. Okay, it spins, but spins, right, doesn't contribute to any change in the kinetic energy. If something is spinning just like this, right, when you add heat to it, right, it will not spin faster. Okay, if you add heat into a gas, then it will move faster, it will rotate faster, but it will rotate faster, but it spins, right, the spin won't change. Okay, can't change the spin. So that's a bit of out of syllabus thing. So for diatomic molecules, your degree of freedom will be equals to 5. Okay, so that is for now. Why do I say 5? Why is it not just these two? Why not just these two? Is because if you are having diatomic molecules, you also have the particles moving in translational motion as well. So it's just like what I'm trying to draw here. So if it's a diatomic molecule, the particle will still move. You will still move to the left-right direction. You will still move in the up-down direction. You will still move in the front-back direction. So that's for diatomic molecules. So let's move on to the next type of molecule, which we have more than 2 atoms forming the gas molecules. If more than 2 atoms forming the gas molecules, you call it polyatomic gas molecules. Poly means many atoms molecules. So you have many atoms forming the gas molecules. So what's the difference if you have more than 2 atoms forming the gas molecule is you unlock another rotational axis. Okay, so how does it work is let's say just now it was diatomic molecules. Now if I add on another third atom to form a polyatomic molecule, now you can see that the gas particles, the gas molecules can still rotate like this. Can still rotate like this. Okay, but there's one more rotation which is like this. Okay, one is like this, one is like this. Okay, the other one is like this. So I have this axis done, then I have this axis done, then I'm left with this axis. So this axis move like this. Okay, so that's another rotational motion. Okay, so there are 3 degrees of free. There are 3 rotational axes right now. So because you have 3, you need to add on one more degree of freedom. So you have one more kBt. But this time this kBt is contributed by the molecules having one more rotational axis. Okay, so the new rotational axis will be in this omega x direction. So you rotate like this. So this is the properties if it's a polyatomic gas molecule. So as usual, these polyatomic gas molecules can also move in translational motion as well. No worries about that. Okay, so let's call this thing polyatomic. So once you have entered the polyatomic realm, you unlock one more rotational axis. So one more degree of freedom compared to diatomic molecules. Okay, so that's what we have for monatomic, diatomic, and polyatomic gas molecules. So now we have contribution of kinetic energy on average due to translational motion, and we have contribution due to rotational motion. Okay, so all these I'll call it K rotational, ROT. Okay, so you unlock 2 rotational axes if you are a diatomic molecule, and you unlock one more rotational axis if you are a polyatomic gas molecules. So that's most of it. Okay, so on average kinetic energy will be something like this. So depending on what type of gas molecules you are, you get different amount of kinetic energy on average. So now I'm going to move on to another concept called internal energy. So internal energy is still based on principle of equipartition of energy. But before we discuss more about internal energy, so let me write down the definition first. Okay, so that's the definition of internal energy based on mechanics. Okay, internal energy is the sum of kinetic energy of all the constituent particles. Means that all the particles that make up the gas, in our case, all the particles that make up the gas, we sum up all the kinetic energy. So it's the total kinetic energy plus the sum of potential energy due to interaction between these constituent particles. So we add up all the kinetic energy and we add up all the potential energy, and that will be our internal energy. So this one you might need to relate it to something that you learn in chemistry. Okay, so if we have a gas molecule which made out of more than one atom, then you have molecular bonds in between the atoms that bond them together. So this molecular bond, sometimes it can be a covalent bond. Okay, most of the time it will be covalent bond. So another kind of interaction between gas molecules is if you have different gas molecules. This is one gas molecule, this is another gas molecules. Not that they are different, but they are separate molecules. This is one molecule, this is another molecule. It can be molecules of the same kind as well. So if you have two molecules here, these molecules will also interact with this molecule as well. So the kind of interaction between molecule and molecule, we call it intermolecular force. So between molecule and molecule, we call it intermolecular force, IMF. Within one single molecule, the interaction between the atoms, the bond between them, we call it molecular bond. So there's two types of interaction available if you're talking about potential energy. We are now entering internal energy, so we will no longer use this anymore. We will change it to internal energy U. And since the kinetic energy, we are asking it for all constituent particles, it means by we are not doing it for a per particle kind of stuff anymore. It's no longer per particle, it's for the whole gas system. So what should we do is we should take all these 6 things here, if you add them up together, it will be the kinetic energy of a gas molecule on average. It will be the kinetic energy. Okay, kinetic energy consists of translational, rotational, and vibrational, but that's another issue. So we have translational and rotational kinetic energy. If you sum them up, that's the kinetic energy of a gas molecule on average. But now, since you want the sum of kinetic energy, you want the total kinetic energy of the whole gas systems, it means by you should take the kinetic energy of one molecule, multiply by the number of gas molecules that you can find in the system. That's why you multiply it by n. Okay, so if you are a monoatomic gas molecule, you multiply n with this part of the equation. If you are diatomic, then you multiply until this part of the equation. If you are polyatomic, you multiply until this part of the equation. That's internal energy. But this is just the kinetic energy part only. Later, we need to discuss the potential energy part. So for kinetic energy part, you have to multiply with the total number of gas molecules in the gas system. Okay, so this is what we have. This is only half of the kinetic energy. We still haven't talked about the other half, which is the potential energy half. So just now I say I want to go to IMF first, the intermolecular forces. So intermolecular forces, for our case, we don't have intermolecular forces, because that's the assumption we make when we use the kinetic molecular model. Because kinetic molecular model assumes no intermolecular forces. Okay, if you remember, they say there's no attraction between the particles when we are talking about kinetic molecular models. The particles don't attract each other. So if they don't attract each other, there's no intermolecular forces in between them. If there's no intermolecular forces in between them, there will be no IMF. So if there's no IMF, that means there's no potential energy due to IMF. So this should be the potential energy due to IMF, and it's equals to 0. Okay, so but there's one more thing that we have. We don't just have this. Once our molecules get hot enough, get into a very high temperature, what will happen is it will start to vibrate. When it starts to vibrate, the molecular bonds in between them, they will start to stretch and bend. Okay, stretch means by these two molecules here will get closer, further away, closer, further away, closer, further away, closer, further away. They will be like this. So this is stretch. Then bend, it will be this molecule may probably bend like this. So you bend like this as well. Okay, so there's two types of vibration that might occur: stretch, or it might bend. Okay, so this stretch and bend of the molecular bond, actually we call it vibration. So vibration, right, it causes one more degree of freedom. Okay, and this degree of freedom, we call it vibration. So let's draw it out, the molecule first. So you have a gas molecule, and these gas molecules will stretch and bend. Okay, so you you stretch, you get further away, or bend. Okay, I won't draw the bend, so let's just draw it like this to show that it's vibrating. So like I say, it will contribute to another one more degree of freedom. So degree of freedom, one more degree of freedom means by you have another kinetic energy of 1/2 kBt. Okay, so let's write it down this as our kinetic energy due to vibration. But like I say, there's bond in between them. So if you can think of the molecular bond between them as spring. Okay, so you have two atoms forming one gas molecule, and you can think of it as a spring connecting between them. So if you stretch and compress like a vibration, so the stretch and compress actually causes elastic potential energy if you imagine it as spring. So actually this motion, this vibrational motion here, will also causes will causes another potential energy as well. We can think of it as analogous to the elastic potential energy, but no, it's not elastic potential energy. It's just potential energy, but it's due to vibration. So how much is this potential energy? If we learn about it, this is actually similar to simple harmonic motion. So if you refer back to the simple harmonic motion, you will see that the graph of kinetic energy, which is like this, and the graph of potential energy, which is like this, you'll find that if you take an average of the kinetic energy and the potential energy, they will be the same. So actually, if kinetic energy is 1/2 kBt, the potential energy will also be 1/2 kBt. Okay, this relates to something that you learned in SHM. So another 1/2 kBt because of the potential energy of vibration. Okay, so let me write down. This kind of vibration only happens when our gas molecules is in very, very high temperature. So I would like to say that if it's monoatomic particles, then the degree of freedom will be F equals to 3 plus another additional 0 due to vibration. Because there's no molecular bond. If there's no molecular bond, you can't have vibration. Monoatomic is a single atom. So if it's a single atom, how do you vibrate when there's no molecular bond? You can't. So there's no additional degree of freedom. But for diatomic gas molecules, you have F equals to 5 plus another additional 2. The additional 2 is due to the kinetic energy of vibration and the potential energy of vibration. And next, polyatomic. Again, it's more than one atom forming the gas molecule. So if more than one, then you can unlock the vibrational kinetic energy and potential energy. So the degree of freedom will be 6 plus 2. Okay, all this can only happen at very high temperature. Okay, how high is the temperature? When I say very high, if we talk about hydrogen molecules is diatomic, right? H2. So for hydrogen molecules, you see this to be greater than 750 degrees Celsius, if I'm not mistaken, either degrees Celsius or Kelvin. Yeah, so it's a very high temperature. Only you reach that high temperature, only you are able to unlock vibrational motion for these particles. If the temperature is not hot enough, you won't be able to unlock this vibrational motion. It will not vibrate if the temperature is too low. Only for, let's say for hydrogen molecules, if it goes over this 750, then only it will start to vibrate. Only the vibration will contribute to an additional kinetic energy and potential energy to the internal energy of the gas system. Okay, So this, we can still do one more bracket here to close up the whole bracket, because everything will have to be multiplied by the number of gas molecules in the gas system. So okay, before we finish, I just want to let you know really clearly, these things that I draw here are all degrees of freedom. Okay, one more over here. All these things that I put in square here are actually degrees of freedom. So you can see how all the different motion unlock actually contribute to another freedom for you to move. So we usually represent it by F. Okay, so all the numbers of F are already listed down here. Okay, so that's all for this video, and that will wrap up our discussion of principle of equipartition of energy, degrees of freedom, and internal energy. Thank you very much.